VLSos here. This is a video lesson on undoing functions. We're familiar with the idea of undoing. Here we have a simple equation. If we wanted to get the variable x by itself, we would undo multiplying by 2 with the inverse, dividing by 2. But what happens when the variable has many more operations being done to it? In this case, 3 operations, subtracting 1, cubing, and multiplying by 2. Well, we can find a function that will undo those 3 things at once. If we think of this as a function and go through the process of finding the inverse of f, the inverse of f will be the function that undoes f. Let's find that inverse. The process of finding an inverse was the topic of a previous lesson, but we'll review it here. We want to replace the function notation with a single letter variable, and y is the most typical choice. The step at which the inverse is made is the step in which we swap x and y, domain and range, input and output. If they're exchanged or swapped, then we'll have the inverse. In this case, I'm going to replace y with x and x with y. I have the inverse here, but I want to reorganize it so that I just solve for y. I'm going to do that one step at a time. The first thing I'm going to do is undo this multiplication by 2. I'm going to divide by 2. I now need to do the inverse of cubing, which is cube rooting. So I have the cube root of x divided by 2 on the left, which leaves y minus 1. And finally, I'm going to undo subtraction by adding 1 to both sides. Now, we're used to having y on the left, so I'm going to change sides, and I'm going to replace the y notation with function notation. So I'm going to put y on the left and then put back the function notation. But this is not the f function, it's the inverse. So the function notation for the inverse of f is f to the negative 1 of x is equal to the expression 1 plus the cube root of x divided by 2. Now this is a separate and distinct function. We have a different function notation for it. The reason why we use f is because this function is related to f as its inverse. But we could also choose a different name for the function altogether. In this case, we could say that we could consider this expression to also be the g function. Typically, when we do composite functions, they look like this. In this case, we have a function inside of another one, f composed with g. And our f function and our g function have been defined by this work and this process. I can form the expression for this composite by putting the g function into f. How would I do that? I'd start with the outside function f, 2 times the input x. But in this case, the input is not only x, it's the entire g function. So I'm going to leave some space, and I'm going to finish the structure of the f function. And I'm going to put into that space where x went the entire g function. The g function is the inverse of f. It is 1 plus the cube root of x divided by 2. This expression here is g put into f, or we could say f composed with g of x. I can simplify this. Inside the parentheses, I see that I have the like terms 1 and minus 1. If we combine them, they cancel out, leaving 2 times the cube root of x divided by 2 all to the third. Inside the parentheses, I have a cube root, which is being cubed. Cube rooting and cubing are inverses that cancel each other out. And when they do, it leaves 2 times x divided by 2. and 2 times x divided by 2. The 2's cancel out, leaving x, which shouldn't be a surprise. G was the inverse of f that was found. The inverse of f will undo everything that f does. So when we form a composition, a function composed with its inverse, then those 2 functions will cancel each other out, leaving the domain variable. In general, a function composed with its inverse will undo and leave the domain variable.